Yeah, it comes, man, it does come up on here.
Oh, okay.
So what I would do is, like I said, go to library.
Yeah, you gave me the symbols. I'm not copying his work. I'm just.
No, that's okay. You're allowed to copy down the problem so you can do your work and do it all in the course. Guys are quiet. Somebody died. Well, somebody dies every minute, but somebody you know died. I guess that was a dumb question. Just your soul for the next hour, I guess.
Thank you so much.
One question. You said that when there are 3 variables, so what you do is 2 to the power n minus 1, that will be the number of truth, right?
In the first column.
First column.
In the second column, it will be 2 to the n minus 2.
So it is 4.
Correct. So it'll be 4 in the first column, and then 2 in the second, and then 1 in the third.
Okay.
It just goes by descending powers of 2.
Got
It's
it.
probably the easiest way to remember it.
Got it. Now, is this because, say, for example, is this because of a binary thing? Because it's like, for example, if you had 1, 0, and half. So in that way, would the base be 3?
Right, that would be tertiary.
Tertiary. So in that
Yeah.
case, the base will be 3?
Generally, that's 0, 1, 2, if
Oh,
you were
0, 1, 2.
tertiary. Correct.
Tertiary.
Yeah, and that does exist. They used to actually utilize that. They didn't employ it much, but it did exist. So I generated, when I was in grad school, I generated a mathematical program that would generate fractals based on a tertiary system. So it was actually pretty neat. So I don't know what happened to it. I lost it. And I probably couldn't do it now. Okay, so what I want to do today is I want to finish up our logical forms. I think the only stuff that we have left to do with logical forms is go through the statement forms with the truth table and then do the Boolean algebra stuff. And then I wanted to focus mostly today on argument forms, which are a little bit different than our statement forms. And then that should be everything that's on the first assignment. So our first assignment is going to be due at the beginning of class on September 7th. Okay, so over the weekend, as you guys are working on problems, if you encounter a difficulty, email me so I can try to help you guys out. Check back on the announcements. If there's a tough problem that I keep getting emails about, I might just post like a little part of the solution to it that where everybody gets stuck. Okay? So questions before we get started, guys? Okay. So correct me if I'm wrong, but I believe last time we ended up where we proved one of the statements to be true or a Boolean equivalency. And I think we just left off with the second one, so I said we'll finish up that one this time. Okay? So somebody remind me, because I forget things and it's been 2 days. What do I have to do to verify that these two statement forms are indeed logically equivalent if we use a truth table?
Left-hand side equals right-hand side.
Correct. We're going to make a truth table for both of the sides, and then we're just going to determine whether or not the two sides are going to be equivalent. Okay, so let's go ahead and work that through. If I focus on the right-hand side, I think what I might want to do is work inside the parentheses first. Okay, so I think the first column I might make after I set up the table is I might start with P and Q. Okay, and you guys remember from last time that for a conjunction to be true, both of the statements must be true. Okay, so true and true leads to true. True and true leads to true. And then I believe the rest of these are going to be false because each of the remaining 6 columns or rows contains at least one false for P and Q. The next thing that I'm going to do is I'm going to go ahead and say P and Q or R. Okay, so now I've done what's in the parentheses. Now I have P and Q quantity or R. Okay, so now we have a disjunction. And correct me if I'm wrong, guys, but for a disjunction to be valid, only one of the two statements must be valid. So if I look at the first row, okay, I'm just looking at these last 2 columns, and as soon as I see a true, I'm going to stick a true as the output for this. Okay, so true here. I see a true in the second column, true in the first column, nothing's true, true, false, true, just like we did last time, all we're doing is we're just kind of building out the statement. Okay, so let me give you guys a moment to make sure that's okay. But are there any questions I can answer about how I designed either of those two rows? And it might have been a couple days since you guys have looked at this. So remember, conjunction, both must be true. Disjunction, only one of the two, or both could be true. Okay? So what we have now is we have our right-hand side, or actually our left-hand side. Now what I have to do is I have to build the right-hand side. To build the right-hand side, we have our two parentheses. So what I'm going to do once again is I'm going to work inside parentheses. So we have P or R. Then we also have Q or R. And eventually what we want to get to is we want to get to P or R and Q or R. Okay? And that's going to eventually be our right-hand side. Okay. So, sir, please.
On my paper, A and B are the same question.
Are they the same question? Well, that's not good, because now I'm just wasting 5 minutes doing this. So, I apologize, guys. So I guess, and that's everybody else as well, I'm assuming, unless you just got a special paper, which I doubt it. So, I'm sorry about that, guys. What I'll do is I'll make up a new problem, and I'll post it on Blackboard for you guys. Okay, so that way at least you guys have 2 examples of this. So, my fault, guys. I apologize. Not trying to waste your time. Okay, so we already know that this works. Okay, what I did was I cut and paste the object, and I just forgot to change it. So. Okay, so we already know it works. So sorry to waste your time. Okay, so more of a waste of time. The next method to be able to verify that Boolean statements are true, or these sorts of argument forms are true, is we can use something called Boolean algebra. Okay? So what I want you guys to do is the other sheet of paper that I gave you guys with the basic logical equivalencies. Okay? Pull that out, because these are going to be the rules that we need to be able to utilize to verify this by Boolean algebra. Okay? So, for right now, don't worry about the rules of inference. Okay? We're going to use those at the end of today. Okay? But for right now, we're just worried about these basic logical equivalencies. Okay? The way to think about these problems is you find the rule that matches and you just execute the rule. Okay? And also, I want you guys to think of P, Q, and R. Don't think of them always as being P, Q, and R. Just think of them as like placeholders. So P is a variable, Q is a variable, R is a variable. That means there are 3 distinct arguments right there. Okay, so that's all those are. They're just 3 distinct statements for us to look at. Okay? So let's take a look at this first animal right here. Okay, so we have P or bracket, and I'm going to have to write this up, I apologize. Not quantity P and not Q. And we're claiming that that equals Q. Okay, hopefully. Now, we could use a truth table to be able to do this if we wanted to. Okay, but let's see if we can use the Boolean algebra. You guys know that with regular old algebra, you work inside parentheses. Okay? So, if I was to ask you guys to use one of the rules that's on this sheet at this point, okay, and we're working inside the parentheses, okay, does anybody think they might know one of the laws that's on here that we could utilize to maybe simplify what's in the parentheses?
Distributive?
Not the distributive law, unfortunately. Good try. You're on the right track, but it's not distributive. De Morgan's law, okay? Guys, take a look at De Morgan's law, which is the third from last one. Okay, it's almost like a distributive property, which is why you may have confused it, sir. But that's okay. De Morgan's law says that if you have a negation on the outside, you can take it and almost distribute it, okay? So this is going to turn into, by De Morgan's law, P or bracket, this hops over, so not P. The and flips to an or, and then we have not Q. And that's supposed to be equal to Q. And each time you guys perform an operation, make sure you write what step you utilize to get to that point, okay? So again, all you guys have to do is just figure out which of those you're using, and then just write the step. Okay, so does that make sense, guys? That's easy, okay? I think the next step is almost like I'm going to beat you upside the head step, okay? So not that I'm going to beat anybody upside the head. So, sir?
So not Q, that becomes Q, right?
That's exactly right. Not Q becomes Q. Now we need a justification for that. So what rule is that, guys, on the sheet? double negative law, right? Okay, as soon as you guys see a double negative, you guys have been programmed since you're like 5 years old to see two minuses in front of itself. So we have P or, not P or Q. And that's supposed to be equal to Q. Good. And that's our double negative. Anytime in this class, if you guys see a double negative, you don't actually have to show that step if you just want to skip it, okay? Because I get it's a double negative, almost everyone on earth gets a double negative that sees this. Okay? At this point, guys, there's only one rule that we could possibly use to get to our answer. Okay?
Distributive.
So, not distributive,
No,
okay? And you're close. But notice that the two logical connectors are the same. In the distributive property, one's an OR and one's an AND. So basically, you need three statements joined by the same logical connector.
Absorption.
Not absorption, because again, I think this one would have to be an AND for it to be. That's okay. See if you guys can find a law where you have two of the same.
Why does the symbol change from an and to an?
Oh, because when you use De Morgan's law, De Morgan's law says that it does flip over.
Oh.
Okay? Do you see
Associative.
that, sir?
Yeah.
Okay,
I
cool.
see it.
Sir,
Associative?
the associative law, right? The associative law is the only one where you have the same logical connectors. So let's just move those brackets over. So this becomes bracket P or not P or Q is equal to Q. So this is our associative. Nice. Good job, guys. And then I believe that there's something right on the worksheet that says P or not P. Okay, so what happens when you guys see P or not P? What law does that fall under on the worksheet here? Negation law. Okay, so negation law, take a look at that one. Okay, that's like the fifth one down or sixth one down in the middle. If you have P or not P, that's equal to T. And guys, what does T mean in our class?
Truth.
Tautology, right? A truth. Okay? So whenever you guys see like a T, that just means it's a tautology. Okay? So we're going to have, this is T or Q is equal to Q. Okay? So that's our, we said negation. And then there might be a law that has T or P or T or Q in there. It probably has T or P in there. Okay? Remember, P is just a placeholder. It can be whatever variable we want. Okay? So what law do we have there, guys, that says identity law? Okay? Take a look at the identity law, guys. It says that if you have P and T.
Yeah, the T or.
So unfortunately, it's not the identity. You're close.
No, but it's a P or C.
Right, but we don't have a C, we have a T.
Okay.
Keep going down, you're really close. It's going to be the universal bounds law,
Universal.
okay? You're on the right track, just make sure the connector's on the right
What
side.
is C then?
C is contradiction.
Oh, contradiction.
Okay? So remember guys, whenever you see T, it's tautology, C is contradiction. Okay? That's a good question, okay? Because we didn't define those, I don't think. But you're absolutely right, guys. By universal bounds, Q is equal to Q. Okay. So this is valid. All right.
Do you have to memorize this or are you going to give it
No,
back?
sir. Okay. If you want to memorize it, you're welcome to. Okay. I'm not going to stop anybody. But as long as you guys don't write anything on this, either front or back, okay, other than maybe I hate Chris Jones's face, that's fine. I don't care about that. But anything of use, okay, don't write it on there. You're certainly welcome to use this for an examination. Okay. All right. Guys, this is a fairly difficult thing to do, by the way. Okay. So a lot of students have a lot of trouble with this. The only way to get good at it is just keep reviewing it and practicing it. Okay, so we're going to look at a couple more of these. So if you didn't get the first time, we'll look at a few more. But my suggestion, guys, is to make sure you have the logical connectors, make sure it matches up almost exactly. Okay. All right, our second example. Okay, a little bit uglier. So not quantity, P or not Q. And then we have an or, not P or Q, and Q. And that's supposed to be equal to not P. Okay. So, again, I'm hoping the first couple steps might be fairly obvious, and then it might get a little bit tougher from there. Okay? So, does somebody think they might know what the first step is for this thing? Go ahead, sir. It's De Morgan's law again. Okay? If you have a not on the outside of parentheses, kick it out with the De Morgan's law, no matter what. Okay? It's the best thing you guys can do to start this. Okay? So, by De Morgan's law, The not goes inside the parentheses, so it's not P. And remember, the or flips over and it becomes an and. I'm just going to write Q in there, even though it's technically not Q. All right? I just don't want to waste a whole step writing not Q in there. Okay? And you guys know it's a double negative. Okay? You guys know that all your life. Okay? The second set of parentheses remains exactly the same. So not P and not Q. And that's supposed to be equal to not P. Okay? So that's De Morgan and double negative. All right. Everybody in here can do that. I know you guys can do that. All right. The second step, I think, is very sneaky. Okay. The last problem we had, it was just like brute force. This one needs a little bit of finesse with it. Okay. Does anybody think they might see a rule that follows the pattern to where we have an and in parentheses, an and in parentheses, and then an or on the outside of those two parentheses? And if so, what law is that?
Distributive?
It is the distributive law. Very nice, gentlemen. Okay? Take a look at your distributive law, guys. Okay? It's third one down. And we're actually looking at the first of the two distributive laws. It has P and Q or P and R. Guys, what we're going to do is we're not going to distribute, we're actually going to go backwards, and we're going to actually factor out the common term. Okay, so it's actually logical factoring, if you would. So if you guys were to go backwards from the distributive law, okay, so let's just go ahead and write that up, that this is going to be equal to not P, and this is our distributive law. Does somebody think they might know what the, and I'm going to say this in quotation marks, the factored form of this might look like? In other words, going backwards. So we're looking at the right-hand side, and we're trying to make it look like the left-hand side. Anybody think they might know that?
Not P times not P becomes P, right?
So, well, it's still going to be not P, because you're just factoring it out.
Okay.
Oh, I see what you mean, right. In this problem, not P equates to P on this worksheet. Yes, sir. Okay,
Yeah.
I see what you're saying. That's correct. So, anybody want to take a guess and they think they might know what it is? Go ahead, sir, please.
Not P and then in parentheses Q or not Q.
Perfect. Thank you, sir. Excellent. Okay. Think of it like factoring a common factoring. Okay? Notice that there's a common not P. Notice that there's a common and. So basically what the gentleman did was he factored out not P and then the and what he was basically left with is Q or not Q. Does that make sense, guys? It's just like a greatest common factor. Just smash them together, okay? If you're not good with factoring, sorry, okay? Or you can just use the sheet and kind of try to work your way back. Okay, I think at this point we're basically done. We just need 2 more steps, and I think we've actually executed those steps before. So, can somebody tell me what to do with the Q and or not Q in this, or what law that might be? Yeah, if we look at this, okay. So did you say associative, ma'am?
Yes.
Unfortunately, for this one, we can't use associative because there's 2 different logical connectors.
Negation.
Right, the negation law. Very nice. Okay. Guys, remember over here when we had P or not P? It was a tautology. Well, now we have Q or not Q. So indeed, ma'am, it is a tautology. So we're going to say not P and T, okay, is supposed to be equal to not P. And that's our negation. And then this time, okay, remember last time we used universal bounds because it was an or? This time we're not going to use universal bounds, okay? What's the other one that we need to use because it's an and between there? The identity law, okay? So, again, make sure when you guys are looking at this, make sure the logical connectors match up to what's on the worksheet, okay? So, by the identity law, not P is indeed equal to not P in this one, okay? All right, please, sir.
Going back to the last one,
Yes, sir.
T or not, or T or Q. On this sheet, it says for universal bounds, P or T equals T.
Correct.
So
Wait, well,
why did
wait,
we use
hold on,
Q?
hold on. Oh, it's just, you know what, it should be P or T is equal to P. I'm sorry, make that change on the sheet. Whatever moron put this together must have made a terrible error on that. So let me bring it up and show you guys specifically what the gentleman caught. the moron that made this sheet, okay? Under universal bounds, instead of it saying P or T is equal to T, change that, and this should be equal to P. Okay, thank you for catching my moronic, or whoever's moronic thought it was making this up. Okay, I apologize, guys. Okay.
I assume it's the same.
And it's the same thing on this one. It's P. Yeah. Well, P and C. I'm gonna have to look these over. Yeah, you're right. P and C should be a contradiction. P or T should be P though. So this one's correct. This one's all good. Oh shit. Sorry guys. Now I'm confusing myself. Okay, but that one's good. But the other one should be a P. I apologize. Thank you, sir, for catching that. Okay. So, questions about this Boolean algebra stuff? All right. What are the trade-offs between truth table and Boolean algebra? Let's talk about that. All right. Like, when would you guys use a truth table as opposed to Boolean algebra? Because they both do the same thing, right? We could have proved both of these with a truth table. Andre?
I feel like you'd use a truth table if the problem you're working on isn't as long.
Correct.
You can do bigger ones a lot quicker.
Right, because you can bully it, right? You
Yeah.
can just do brute force. That's the trade-off, okay? Truth table is just brute force. It always works, but if it's a long statement, you're going to be sitting there for a long time. If you're good with Boolean algebra, you can literally probably do the problem in a minute, okay? So it's much less taxing to do it if you're good with it, okay? So I'm just presenting both of these to you guys. On the examination, I'm going to be specific. I'm going to say proved by truth table or proved by Boolean algebra. So you got to know both of them. Well, you don't have to. You'll just get that problem wrong if you don't. Okay? All right. Here's what I'd like for you guys to do. Okay? This is an important problem. Okay? It's a tough problem. So I want you guys to try letter C. Okay? I know it's a difficult one, but work inside the parentheses first. Okay? I'll give you guys about 5 minutes to work through it. If you want to work with the person next to you, that's great. If you think the person next to you sucks, then maybe you suck and you're the problem, okay? But give it a shot, okay? Let me know if I can help you guys out with whatever I can, okay? Yes, sir, please.
I showed up late one day. I never got one done.
Oh, you need one of the sheets. That would be helpful, wouldn't it?
If you wouldn't mind.
Not a problem. There you
Thank
go,
you so
friend.
much.
Not a problem. Do you need anything else, or syllabus, or
I got the.
you got that? Okay, did you get the
I
syllabus?
can read online if I need to know.
There you go, my friend.
Thank you.
You're welcome. If you guys need assistance, don't be afraid to ask. I won't bite your face off. Unless you're into that weird stuff. Oh, right, yeah, it has to be the exact form that's, is that what you're asking, like if it's?
Same letters too, same.
Oh, correct, it has, well, it doesn't have to be the same letters. So it just basically has to be 3 different statements. So it could be like a P would be your P, the Q would be your Q, and then like maybe not P would be your R. Okay, so if you have a not P, that's a different variable. That might, is that what you were asking? Maybe.
Well, I think nonetheless I figured out that I can't do that.
Okay. Welcome to being married. Yeah, this is one of those things you guys might just have to go home and hash out for yourselves for a half hour or an hour. It's just tough stuff. Sorry. But it's not physics, thank God. Sorry. You need a hug then. Guys, a couple more minutes to finish up, and then we'll go through our answer together. For those of you guys that arrived at an answer, how many steps did it take you? Just curious. That's what I did when I did it in my head. I got 5 steps. And if you guys did a truth table for this, oh Jesus, that would be hideous. No thanks. Guys, so let's try to formulate a solution to this, okay? So I asked that you guys work inside the parentheses first, all right? Although you could have gotten the answer by using De Morgan's property first and sort of like allocating the not to both of those, although it might make it a little tougher to do that, okay? I always tell people work inside parentheses if you can. So, for those of you guys that worked inside parentheses, what rule did you use to maybe simplify this expression from what it was?
Distributed?
The distributive property. In fact, it's just like what we did over there when we factored out the not P, okay? So, sir, can you tell me when you were done with your distribution, what did that look like, please?
Not P, then and, then Q, or not, or Q.
Or not, oh yeah, or Q or Q.
Q.
Okay. So that looks good. Okay. All right, so is that good with everybody? Any questions as to how he did that? He basically factored out the not P, all right, and he was left with Q and Q. Okay, so we're also still left with the P and Q, but that's not a big deal. Okay. So I'm hoping that now that we've gone through and factored that by using the distributive property, that it might be fairly easy to see what's going on inside. Okay? So guys, if you have two of the same thing right next to each other, doesn't it look like if I have black pen or black pen, I've got black pen, okay? So it's the same thing. If I have Q or Q, that should be equal to Q. And I think there's something on your sheet that has P or P, that should be equal to P. So can somebody tell me if it was Q or Q, that should be Q. What rule is that, by the way, sir?
I was going to go back up to the very top. The second part, it's not P and not Q.
Oh, I made a copy error, which would screw the whole thing. That's strike two. Wait, one more strike and I guess I have to go over to the beach. Sorry about that, guys.
So that changed the second one too.
Yeah, that would change this, which would make Okay, there we go. Sorry about that, guys. Okay. So if I have Q or not Q, it's the same thing as either P or not P. So I think we said that this is going to be a tautology, isn't it, guys? Okay.
Negation.
So this will be a T. And is that the negation law? Okay, thank you. So this is going to be not P and T or P and Q. Okay. And that's our negation law.
Should there be, you have not outside the parentheses, but should there also be another negation?
Right here. Yep. All these copy errors, man, suck. So it's a lot easier on a piece of paper, I think. So, but thank you guys. I really appreciate that you're checking me out. Wait, that sounded weird. That you're checking my work out. Okay. All right. If you look inside the parentheses, not P and T is going to end up being not P. So we have not P or P and Q is equal to P. And what was the rule where you have P and T? Was that the identity? Okay. So if you have something and a tautology, it's always going to end up being the something. Okay. So this is going to be our identity property. I think it's almost leading you upside the head that not P is just going to be P. Okay, so we have P or P and Q. And by the way, you could have skipped this step and you could have just gone right down to this. Like you could have gone from line 3 to line 5 if you just wrote in the double negative in there. Okay, you don't have to do that, but it might be helpful for you guys to see all the steps. Okay, so this is our double negative property. And then finally, I think there's a property on the worksheet that exactly gives this identity right here. So what's the last law that you guys would need? The absorption law, right? If you look at your absorption law, P or P and Q just becomes P automatically. So this is P is equal to P, and that's absorption. Okay. So, generally, okay, I've taught this course for, oh geez, this is probably the 20th time I've taught this course. All right, this is one of the most difficult things at the beginning of the course to do. Okay, so if you're a little bit overwhelmed with this or blown away with it, make sure you guys go home, look over it for a good half hour or hour. Okay, it's definitely a difficult topic. Work through some of the homework problems. If you need help, come and see me. Okay, so, but I'm just saying it's not like one of those things where you can just sleep on it like a truth table and get it fairly easily. Okay. All right. Questions I can answer about the Boolean stuff before we move on. Okay, sir?
How do you use a distributive if there's no R?
Oh, that's a good question. When you look at this, see how these two are the same? So think of those as just like P, okay? Because what's actually happening is, if you look at your distributive law, it's just a placeholder. So this is the P. This Q would be the Q. But I want you to notice that these two are different. So this would actually be the R. It's a placeholder. So anytime you have anything that looks different, it's a different variable for that. Okay? Does that make sense?
Yeah, that makes sense.
Okay. So yeah, when you guys are doing this, think of the P, the Q, and the R as just placeholders for anything unique. Okay? That's a good question. Okay? I think the sooner you guys realize that and see it, the easier that these will be to try to work down. Okay? That's a really good question. Thanks. Okay. Other questions, guys, I can answer for you all about this?
So it's like a follow the PEMDAS, always do the parentheses first.
Yeah, basically, if you think of it like the order of operations, you do your parentheses, you do your nots, okay? Because in computer science, does it not have one of the highest precedences as well, okay? Your logical connectors, like your ors and ands, have the next highest, and then your conditional stuff. So, and I don't know, like in computer science or whatever, if you guys learned about the order of operation that logic works, but I'll just write this up just in case. But the way that logic works, like precedence, parentheses first, nots, ands and ors, and then if-thens.
Is there a precedence between the ands and the ors?
No, you just go from left to right. It's sort of like addition, subtraction, multiplication, division. That's a good question, yeah. So if you guys ever have like a program that you're reading, okay, or you have to develop a program and eventually some of you guys are probably going to take like algorithm analysis and you have to figure out like how fast the program runs. This is important to figuring out how fast the program runs because you have to figure out the order of operations to that. Okay, so, but I guess nowadays it really doesn't matter how fast it runs because the computers just are so fast. So it's not like 1996 where I crashed the computer every time I tried to run something. So regardless. Okay, so any other questions I can answer for you guys about this before we move on? Sir, please.
Can you do a different example with that for doing the Morgan alters?
Oh, I see what you mean. Do you mind, okay, can you email me? And what I'm going to do is I'll post it on Blackboard for you. Would that be okay?
Yeah.
Okay, because just email me like specifically what you're looking for, like an example of the De Morgans first, and I'll just make one up for you and post it on Blackboard. Yeah, it never hurts to see more of these, I understand, but unfortunately we only have an hour and 20 minutes together, but I certainly will do that for you, okay? All right, other questions, guys? Okay. So the next thing we're going to look at, guys, is something called converse, contrapositive, and inverse of a conditional statement. Okay. Throughout the course, we're going to be utilizing these ideas. Okay. So if I have a conditional statement, okay, like P implies Q, the converse just flip those around. Okay. So let's say if I study, then I will pass. If I flip that around, if I pass, then I study. That's the converse of that. Okay. So you're just flipping it around. The inverse takes the negation of both the statements. So if I study, then I will pass. If I don't study, then I will not pass. That's the inverse of that statement. The contrapositive both flips the statements and negates them. Okay? So that would mean if I study, then I pass. If I don't pass, then I did not study.
Oh, so the conclusion goes before.
Correct, right. The conclusion and then the antecedent would be flipped. Okay? All right. Of these three, the contrapositive is actually logically equivalent to the original condition. Okay, so in fact, in the second part of the course, when we start to do proofs, we're actually going to do something called an indirect proof by contraposition. Okay, so just put this on the back burner for now. I'll probably ask you guys again later, which is logically equivalent to the original statement. It's the contrapositive. And by the way, if I wanted to prove that, couldn't I just make a truth table and prove it by truth table? Okay, you guys can go home and do that if you want to, or you can just believe me. Okay, but probably believing me is the good one. Yes. All right. So let's just do a couple examples. We're going to write the converse, inverse, contrapositive, much easier than the Boolean algebra stuff. Okay. So if I study, then I will pass. I just said that one out for you guys, but let's just write it up. So if I want the converse, I just flip the conclusion and the antecedent. So for the converse, that's if I pass, then I will study. Or then I study, whatever you want. The inverse of that statement says that if I do not study, then I will not pass. If I don't study, then I will not pass. And then the contrapositive, that flips them. So if I do not pass, or if I don't pass, then I do not study, or then I don't study. All right. So, easy as it gets, right, guys? There's no numbers in that problem. Okay, just logical stuff. So, one of the things also, guys, remember, it's still a conditional statement, so you still need if-then in there. Okay, I always see a lot of students forgetting that it's still conditional, so you should write if-then in there. So don't forget, guys, it has to stay if-then. Okay. This second one is a little bit trickier, and generally students get this wrong because they forget to implement something. So it says, if I'm tall, then I drink milk or I'm good at basketball. Okay? Most people get the converse of this correct. Okay? So if I was to ask you guys for the converse of that statement, okay? Somebody tell me what they think or what they know the converse of this to be, please.
If I drink milk or good at basketball, then I'm tall.
Perfect. Okay? So if I drink milk, hopefully it has Kahlua in it. If I drink milk, is it Friday yet? Or I'm good at basketball. Wait, why does it have to be Friday to drink? It's a Wednesday, right? Yeah, I can drink. Cool.
Happy Wednesday.
Every Wednesday, yeah. Right on. If I drink milk, or I'm tall, or I play basketball. Then I'm tall. Okay. And generally, most students get that one correct. Okay, that's not too difficult. Unfortunately, what happens is when they go to take the negations and they try to do the converse, I'm sorry, the contrapositive and the inverse, that's where students go wrong with this. Okay, so if I was to ask you for the inverse of this, okay, does somebody think they might know what the inverse of this is going to be?
Right.
So go ahead.
So if I am not tall,
Okay, I like it.
then I do not drink milk and not good at basketball.
So if I am not tall, then I do not drink milk. Don't drink milk. And then you said one word in there that elated me.
And
So, end. Okay. Now, how come it goes from or to and, sir?
for the law, that negation law, that
Not the negation, but it rhymes with Alorgans.
De Morgan's law.
De Morgan's law. There you go. It was right on the tip of your tongue. Excellent, sir.
Thank you.
Okay. So, and. Okay, so remember, anytime you have a logical connector and you're taking the negation of it, you have to flip that connector. So instead of an or, then it becomes an and. I am not good at basketball. Does that make sense, guys? And this is where students go wrong with this quite often, okay? If I had $1 for every time a student did this wrong, I wouldn't be teaching anymore. Well, actually, I'd probably still be teaching, but I wouldn't be as poor. I'd just be slightly poor, okay?
You'd have an extra beer every week.
What's that, sir?
You'd have an extra beer every week.
Absolutely, more than a couple. Well, cheap beer. So, yeah. All right. And then obviously, guys, once you know that, the contrapositive is very easy, okay? In fact, for the contrapositive, all we do is we just flip the order of the inverse, okay? So, if I don't drink milk, and I am not good at basketball, then I am not tall. Let me give you guys a minute to copy down my chicken scratch. Okay. But does that make sense to everybody, guys? Any questions I can answer about that? Okay. Again, later, the reason we're doing this is because later in the course, we need to be able to write the inverse, we need to be able to write the contrapositive. Okay, so it's not like this thing that we do once and it's going to go away. There's going to be proofs that we have to do this within. Okay. All right. So the last thing I wanted to talk about today, which is going to take up a good chunk of what we have left, is going to be the arguments and argument forms. Okay. Basically, an argument is going to be a sequence of statements. Okay. So an argument is going to be a sequence of statements. An argument form is a sequence of statement forms. Okay, so an argument form. And just to remind you guys the difference between a statement and a statement form, okay? This is a statement. This is a statement form, okay? So statement is just literally a variable. Statement form is when we start throwing the logical connectors in, okay? So it's not really much different than one another. Okay, so basically a statement form, or an argument form, basically is just comprised of statement forms. And this is really what we're going to be looking at.
What's the difference between statement and argument?
Oh, well, the argument is actually going to be something that looks like this. Okay? Where you have a sequence of these. And then based on the sequence, and again, we're going to figure out these are valid and invalid, okay? So this is an argument. But basically, if you wanted an argument would be this: P, Q, R, therefore T, okay? That would be an argument. This is an argument form because it starts throwing in logical connectors, okay?
Okay.
They're basically almost the same thing. Does that make sense, sir?
Gotcha,
It's a good
yeah.
question, thank you. Okay. All of the forms except for the last one are called the premises, okay? All arguments are based on premises, okay? So, these are the premises. And then the final statement in this, or the final statement form is called the conclusion, okay? And what I put up here in a box, this is a very basic argument form, okay? The first two statements are the premises, the last one's the conclusion, okay? What we eventually want to do is we want to figure out, is the conclusion valid or invalid, okay? So, an argument form is valid if no matter what we plug in for the statement forms, that the conclusion is also going to be true, okay? Now, what I'm going to do, guys, is I'm going to show you guys two ways to verify an argument form, okay? One of which is going to be the truth table, the other of which is going to be able to use those basic rules of inference that are at the bottom of the sheet, okay? So much like proving equality between two statement forms, we have a brute force way, and then we also have a more sophisticated way. Okay, so let's take a look at the method you guys would utilize to verify by using a truth table. Okay, so if I have an argument form like this, I can determine if this is valid or invalid by using a truth table. Okay, so we keep going back to truth tables because they're so fundamental. What we're going to do is we're going to construct a table for all premises in the conclusion. Okay, so we just make a truth table for all three of these statements. Any row in which the premises are true is called a critical row. Okay, so basically all I'm going to do is I'm going to put a box around the critical rows. The conclusion is true in all critical rows. That is a valid argument form. Okay, so basically if you guys can make a truth table, you guys can do these problems very easily. Okay. So let's do this, guys. Let's go through this one, okay? And then I'm going to let you guys try letter B on your own, just in case you guys were to see this on homework or see it again on a test. All right. So let's just make a truth table for letter A. So we're going to have our 8 rows. That's why we don't like truth tables, right? They're a bit of a pain in the ass. I think of truth tables like mowing my lawn. I can do it whenever I want. I don't necessarily like to do it all the time, but it's just painful to do. Sounds like math in general, doesn't it? P, Q, R. And we have our 4 T's. And we have our 4 F's. Blah, 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 blah. God, I have to do this for the next 35 years of my life. Awesome. You can write that on the teacher evaluation. So once we have our truth table together, then what we're going to do is we're just going to go through and we're going to make a column for each of the premises and figure out which are going to be the critical rows. Okay? So I always tell people just go through, okay, do the first one, and as soon as you get a false, just ignore it. Okay? The rest of that row. Okay? So the first premise we have is P implies Q. Okay, now, somebody remind me, because that was, what, like almost 2 days ago. Okay. When is the only time that the conditional is going to be false? Anybody remember, sir?
If the premises is false, the conclusion is true. I'm sorry, backwards.
Yeah. If you have true implies false. Okay, very good. So the only time that the if then is going to be false is if you have true implies false. So true implies true. That's true. True implies true. That's true. True implies false is false, which means we're done with that row. Okay? As soon as you get a false, it's not a critical row anymore. If it's not critical, who cares? okay? Because we only care about critical rows. Does that make sense, guys? It'll make your lives a lot easier, okay? True implies false is another false, so row number 4 goes away. And then as soon as the antecedent is false, you know that the conclusion is going to be true no matter what. So the rest of these are all true. Okay? So at least we've reduced our work by 25%. Okay? Let's see if we can reduce it a little bit more. Okay? Because the next premise that we have is Q implies R. Okay? Same game. What we're going to do is we're just going to say we're going to look at column Q and column R. Anytime true implies false, we're done with that. Okay? So Q implies R, true. True implies false, that's false. So now we're done with row 3, or row number 2 as well. Okay? We have true implies true for row number 5. That's true. We have true implies false for row number 6. So row number 6 has a false, and we're done with it. And then the last 2 of these rows, we have false implies true, false implies false. They have to be true. Okay. So, when it comes down to it, guys, don't we only have 4 critical rows? Okay? And that way we don't have to keep making truth tables for stuff. Okay? Or at least those rows. I apologize. Okay. So, now what we want to do is we want to look at row number 1, row number 5, and then row number 7 and 8. Okay? Those are the critical rows. Okay? Any row in which all the premises are valid or true is a critical row. What we have to do is we have to determine if this is a valid or invalid argument form by checking the conclusion now. Okay? So, I'm going to have P implies R. Okay? So, I have P which is true, I have R which is true. True implies true is a true. So far so good. I have false implies true. Well, that's true. Anytime it starts with a false. And then, guys, the last 2 start with false as well. So these are true. So, because the conclusion is true in all the critical rows, we're done. This is a valid argument form. In fact, some of you guys might actually recognize this as one of the 8 of the basic rules of inference. So look at that sheet that we just used about 20 minutes ago. Which rule of inference did we actually just verify? The transitivity rule. Okay? So this is a way that if you guys ever wanted to verify any of these rules, you just use a truth table. Okay? So, basically we have to answer the question, and this is valid by table. Right. Does this make sense, guys? It's not difficult, okay? We've been doing truth tables a lot for the past couple of days, so I'm hoping you guys are pretty good with that. Alright, so what I'd like for you guys to do, take about 5 minutes, see if you guys can see if letter B works, okay? Or maybe not work, okay? And then we'll go through the answer together.
What was the last blank on the?
Oh, I'm sorry, sir. Back up here.
The
The last fill in the blank.
Yep.
Valid.
Okay.
I'm sorry, sir.
Thank you.
Yeah, if I'm ever moving too fast, yell at me, okay? Because you guys are paying for the course, not me. So I just want to make sure I'm not cheating you on your education. When I worked it through, guys, I only got that 3 of the rows actually mattered in the entire problem, okay? So, and that's definitely helpful because think about, like, I mean, you're eliminating 62.5% of your work by getting rid of those rows, okay? So, when I did this, okay, be careful with the implies, okay? That's the only one that gets messy. But my first row, my third row, and my 5th row are all critical. And if I look at the critical rows, it looks like that indeed the R is going to be true. In fact, you didn't. I made an extra R column. You didn't have to make the R column, right? I bet you most of you guys just looked at this and were like, oh, that's R, duh, I don't need it again. Right? So guys, this does indeed work out to be one of the valid argument forms. Okay? So, by the way, and some of you guys might have seen this before, but does anybody know what structure this is? It's not on your worksheet, but this is it's a valid argument form. I don't know, and I know a couple of you guys might have taken logic before, but if not, this is actually called division into cases. Okay? So basically what this says is that either P or Q is true, P implies R, Q implies R, so that means they both imply that some conclusion is valid. That means that the conclusion must be true. Okay? Later in the course, we're actually going to use division into cases as a methodology for proof. Okay? Because think about, like, if I wanted to prove like an integer statement. Integers are either odd, right? Or they're positive, negative, or 0. Those are division into cases. Okay? We're going to look at different types of cases later in the course. Okay? Regardless. Okay? Everybody okay doing this? Any questions, guys? Okay, Andre and then Art.
What are the different cases that this would be invalid? Like what
Gotcha.
makes it invalid?
So let's say for some reason, okay, that's a good question. Let's say for some reason, and I know this isn't right, but let's say this R, which is the conclusion, is false, right here, in a critical row. That would make the entire argument form false.
Okay, is that the only way that it could be?
Correct, that is the only way, as long as one. I mean, it could be several, okay? But as long as you get at least one of the conclusions in the critical row false, it means the whole thing's false. Okay, does that make sense, sir? They all have to be true, otherwise no good. Okay, good question, thank you, sir. Okay, sir, you had a question. Same question, you just took it from your mind. That's kind of creepy, man. Don't do that again. All right, other questions I can answer. Sir?
I'm just saying, in that case, if we go through and we find the first one false, just stop.
Yep, you got it. That's exactly right. Yeah, don't waste time. I mean, if you guys know it's going to be false, just go with it. Nice, good point. Okay. Sir?
So that true at the second, the seventh row doesn't mean anything?
That's correct.
It's
Because
not critical. And
correct. Right. Because it's not critical, don't care. Okay? And that's why you guys just ignore non-critical rows. Just waste your time. Excellent, sir. Very nice, guys, sir. Good stuff. All right. Other questions, comments? Okay. All right, guys. Let's just take a look at another pair of easy problems, and then we're going to have to suffer through some difficult ones at the end. Okay? These are ones if we actually have it formulated in some sort of sentence. Okay? What we want to do is we want to try to build one of the forms that's at the bottom of your guys' worksheet. Okay? And when I say the worksheet, I mean the basic rules of inference. Okay? So what we're trying to do is we're trying to rewrite the statement or the sentences so that it looks hopefully like one of those, and if it doesn't, it's invalid. Okay? So let's take a look at a couple examples of this as to how we can do this. Okay? One of the first things we ever did in this class was I gave you a sentence, you wrote it in symbolics. Okay? That's what we're going to do right now again. All right. The question is, if Bob answered this correctly, he answered invalid. Bob answered invalid. Therefore, Bob answered this correctly. All right? Let's try to write this argument form symbolically. Okay? I need two statements. What are the two statements that comprise, or what's one of them? Sir?
If Bob answered this correctly.
Bob answered this correctly. Nice. And then you guys just chop off the if because it's not conditional. Nice. So, one of them is Bob answered this correctly. And then, what's the other statement that comprises this argument form? So, sir?
He answered invalid.
He did answer invalid. Okay? So, he answered invalid. Okay? So, just like we did at the beginning of class on Monday, we define statements, okay, using variables, okay? Everybody can do that, okay? All right, let's see if we can write this in one of the forms, okay? So, if Bob answered this correctly, he answered invalid. How would I write that statement symbolically using our definitions?
P implies Q.
P implies Q, perfect, okay? So, if I want to write this symbolically, P implies Q. The next line, Bob answered invalid. How do we write that symbolically?
Q.
Q, right? I mean, it's right there. He answered invalid, so it's Q. Therefore, Bob answered this correctly, which is P. Okay. So, that is the argument form of that argument form symbolically. Okay, does that make sense, guys? That's easy to do, right? We can all do that. What we're going to do is we're going to go back to the basic rules of inference, and we're going to see if it matches. Okay? So, I look at modus ponens. P implies Q, P therefore Q. I have P implies Q, Q therefore P. So it's not modus ponens, right guys? Because those are flipped. It can't be modus tollens because it has nots in there. And then the rest of them don't even have implies except for transitivity, which it doesn't. Okay? What does that mean then, guys? It means it's not valid. Okay? If it is not on there, it is not valid. Okay? So you would say that this is not valid. This is actually a specific type of error. And maybe some of you guys have seen this before. What type of error is this specifically exhibiting? It starts with a C.
Circular?
Not circular. Good try, good try. Converse error. Okay? Remember we talked about the converse where you flip the P and the Q? If this was P then Q, not Q then P, we'd be good. But unfortunately, because we flipped those, this is indeed a converse error. We said that only the contrapositive is logically equivalent. Isn't modus tollens the contrapositive? If you look at that, you're just flipping the order of those. Okay? So, does that make sense, guys, as to how to do this? It's not meant to be difficult. Okay? This is a really easy problem for everybody to do. Okay? Let's take a look at a secondary example. Okay? If I go to sleep early, then I will wake up early. If I wake up early, then I will be energetic all day. If I go to sleep early, then I will be energetic all day. Okay? I believe that we have 3 statements in there. Okay, sir, please.
I'm sorry, I just have a question about
Sure.
this problem.
Yeah.
So I don't understand what was logically wrong with the statement then.
Oh, okay. The order was incorrect in which it was presented. Okay? So if you look at the modus ponens, okay, this is valid. It says that antecedent leads to conclusion. This is the conclusion. This is actually begging the conclusion, or I think maybe you said circular, which is almost, or somebody did, or something like that, which is almost the case, to where what you're doing is you're putting the conclusion before the antecedent, okay? So logically, that's what's happening. You're begging the conclusion, okay? It's almost like when you guys are doing homework sometimes, and you're like, screw this, I'm just going to go to the back of the book and write the answer. That's exactly what this is, okay? It's just skipping right to the answer, okay? So it's a good question. Thank you, sir. Okay. Other questions, guys, before we move on to the next one? Okay. So, like we said, I believe that the next one has 3 statements in it, okay? So I think one of them is going to be, I go to sleep early. So let's go ahead and knock this one out. Okay, so let's say P equals I go to sleep early. Q is going to be I will wake up early. And then R is going to be I will be energetic all day. With enough Red Bull, that's certainly valid. Red Bull and Jaeger, which is basically a speedball whenever you do a Jaeger bomb, because one of them is a stimulant, the other one's a depressant. So, anyway, regardless, so things you really learn in this class, right? Okay, sir.
So when it's nice that we have to actually say what they are.
Yes, sir. Okay, unfortunately you have to define them, and the reason being is because it's linking to computer science, and you guys know when you're building a program, first thing you have to do is define your variables. Okay. All right. So let me ask somebody. Okay, can you guys go through and just tell me what the argument form is going to look like if I were to translate this sentence using the symbols? So what's the first sentence look like? So sorry.
P implies Q.
P implies Q. So the second one?
Q implies R.
P implies Q, Q implies R, and therefore, what does that mean, guys?
P implies R.
We may have seen that earlier today, okay? Guys, which of the 8 of the basic rules of inference does that fit, Don? The transitivity. And guys, how do we know transitivity is valid? Because we freaking proved it, okay? So there's no way that this could be wrong, okay? Unless I just pulled some algebra magic, hocus pocus, and made you think it was right when it's really not, okay? But this is valid by transitivity. All right. So I always tell people, if you can write it symbolically, it's probably a lot easier to be able to determine validity versus invalidity. Okay? The last one, very, very easy. Okay? Homer works at power plant, so P is Homer works at a power plant. And then Q is he sleeps on the job, or Homer sleeps on the job. We'll just say he sleeps on the job. Sounds very dangerous.
Is that Homer Simpson?
It is Homer Simpson indeed. So if I was to ask you guys to build this, okay, the first statement form would be what, guys, for this? P and Q, right? I mean, it's so obvious, P and Q. And the conclusion is, therefore, Q. So all we have to do is just see if one of the basic rules of inference decides to fit that, okay? If I look at my basic rules of inference, I believe that specialization may be the one that fits that, okay? And if you guys wanted to prove specialization, you could use a truth table to do so, okay? So you would say that, once again, this is valid by specialization. Okay, so, any questions about being able to verify either by truth table or by using these basic rules of inference if an argument form is going to be valid or invalid? Okay. If it, by the way, if it doesn't fit one of the forms up here, just assume that it's not going to be valid. Okay, because I'm not going to give you guys anything that's not on this. If you ever needed to in real life check it, you could just use a truth table and verify that.
So the division in the case is an outlier for this?
Yes, sir, that's correct. All right, other questions, guys, I can answer before we move on to the last stuff here? Okay, now, I want you guys to take a look at the very last argument form that we have, or the last couple here. If I were to ask you guys to prove this by truth table, which you could, okay, what would be the problem if I asked you to prove this by truth table?
4, 5 variables.
5 variables, which means how many rows?
32.
32, which means pain in the ass, right? Pain, like absolutely. No way, okay? You guys don't want to sit there and use 32 rows. You don't even want to use 8 rows if you can. So what we're going to do is, instead of a truth table, all these basic rules of inference, we are going to build the basic rules of inference from what's given, okay? So you guys have that sheet, okay? I don't have it, well, I can't look back and forth, but what we're going to do, guys, is we're just going to pick apart the premises to get to the conclusion, okay? So basically, if you guys were thinking of a process for this, okay? You're going to use the premises to build the basic rules of inference. And remember, guys, the basic rules of inference are all valid. Please, sir.
In this case, does T stand for true? Or
I was actually just going to alliterate that. That's an excellent question. In this problem, T is its own unique variable. It is not a tautology in this case. Okay, so I should probably use capital T's from now on. Okay, so I apologize. I'll make sure, like, if it's a homework problem, that I'll make sure that there's no T's in there to try to confuse you guys. I'll try to use different letters, like gammas or something weird like that. All right, let's see how we're going to do this, okay? So, the first thing I think we should do is, let's start with the most simplistic thing that we have in this, okay? Now remember, you can't use the conclusion, Okay, I mean, you could, but you'd be wrong. Okay, so this is what we're trying to get to. Okay, so don't just jump to the not Q. Well, that didn't help, did it? Oh, stupid computer. There we go. Okay. So I want to pick on the easiest thing that I have, and the easiest thing I have is not T, right? It's the most simplistic thing to start with. There's only one other statement that has a T in it. That's P implies T. So let's see if we can build something that looks like one of the argument forms. Okay, so. Does anybody think they might be able to build one of the basic rules of inference from just using the not T and the P implies T? So, Donnie, what do you think, sir? Modus ponens, or modus tollens, right, sir? Okay, so if this is step 1, you would have P implies T, right, guys? And then you have not T, okay? As a result of modus tollens, what is the output then for this?
Not P.
Not P, right? Guys, take a look at your modus tollens. P implies T. If you have the negation of the conclusion, that gives you the negation of the antecedent. Okay, so this is going to be not P. Okay, so this is just your modus tollens. Okay. Remember, these are all valid. So once you get to this, you're allowed to use this as many times as you want in the problem. Okay, so now what we're going to do is we're going to get rid of the not T. Okay, we don't need this anymore. We're going to get rid of the P implies T as well. Okay, so those are off the table. We don't need those arguments anymore. Okay. Now what I need to do is I need to find something with the not P in it.
I got a question.
Sir.
You can start anywhere in the argument. You don't have to follow sequence or something.
No, sir. They do not have to follow sequence. Okay.
Okay.
It's just like you can just rearrange them however you want to do it. Okay.
Gotcha.
So just because it was the third and fourth one down, start wherever you want. Okay. All right. So I have not P, okay? Well, it looks like the only thing that's up here that has a P in it is either not P and R, or not P or Q, okay? So I either have to use something to get me here, or something to get me here. Does anybody think they might have one of the rules of inference, and you have a 1 in 8 shot that could help us? Yeah, this one's kind of sneaky, okay? If I have not P, and that's from step 1, couldn't I have not P or anything else? Okay, let's play peekaboo game. Okay, I have black marker, or I have $1 million behind my back. I'm not lying to you, right? I have not P or something else, right? Now, what's the or something else that we want? Or Q, right, guys? We want to build that statement, and that's by generalization. Take a look at your rules, okay? If you can build something with an or, you can't build an and, but you can build or, okay? So this would be not P or Q by generalization. Does that make sense, guys? Sometimes you have to build a statement, and you can use whatever or you want. In this case, Q helps us out. And then, by the way, this is a therefore. Sorry about that. Okay. Step 3. Okay. We can use not P or Q. Okay. So, wouldn't it seem likely that we should probably use this? Because we already have not P or Q implies R. So we have not P or Q implies R. Didn't we just verify not P or Q is valid, okay, in the previous step? So, we have not P or Q from step 2. So, what can we conclude based on one of the 8 rules of inference, and what's the rule that we would utilize?
Not P or Q.
So we have antecedent, right? And then the previous statement has antecedent implies conclusion. So, anybody think they might see something that can help us? It rhymes with modus, oh, go ahead, sir.
You use modus ponens?
You can, yes, sir. Excellent. Okay? Guys, take a look at modus ponens. It says antecedent implies conclusion. P implies Q. Think of P or Q, or not P or Q, as the antecedent. Think of R as the conclusion. Well, if you have antecedent implies conclusion, if you have antecedent, then you have the conclusion. By exactly correct, sir, modus ponens. Okay? So, like I said, the P and the Q, they're just placeholders. Okay? They can be whatever they want. In fact, they could be a statement form, as long as it fits the form of this. Okay? So, does that make sense, guys, so far? Any questions? Okay, again, this is another one of those tough things. Okay? So, I'm going to get rid of the first. Okay? We're almost done with this, by the way. Okay? Now I have R. Okay? So, doesn't it seem reasonable for me to be able to say, from step number 1, I have not P. From step number 3, I have R. So, for step 4, I have not P, and I have R. Not P is from step 1, and then R is from step 3. So, if I have not P, if I have R, what does that mean that I have? Not P and R, right guys? Okay? It's just like this. If I have black marker and I have blue marker, I have black marker and blue marker. Okay? It's the same thing up here. So, therefore, this would be not P and R. And what's the rule that says if you have two statements, you can conjoin them? Conjunction, right? It's almost like I was trying to give you guys a hint with that. So, conjunction. Nice. Yeah. I know we've only got 3 minutes left, and you guys care less about this at this point. But regardless. Okay. Does this make sense, guys? Any questions so far? We're almost done. Okay. Well, now we can use the 5th line for step 5. Okay. So for step 5, we're given that not P and R implies not S. We have not P and R from step number 4. What can we say as a result of that then? What's the conclusion from that and why? Not S. And how come, sir?
Because P and R implies not S. So
And we have P and R, which is the, yeah. So we have not S. Which rule is that, guys? Modus ponens. Nice. Good job. In fact, it's the same exact structure that we just saw in step number 3. Okay. All right. Well, I think we're done with this because now, our final step, the last, oh, sorry, I meant to cross this out because we're done with it. The last possible premise we have is S or not Q. From step 5, I was told that we have not S. So what does that tell me must be left over? And why? So it says I have either blue marker or black marker. I don't have black marker or blue marker, so then I have black marker. Go ahead.
It would be modus tollens because of the, it would be Q.
It would be not Q. And unfortunately, it's not modus tollens, Andre. Close, okay? Because it doesn't have an implies in there. Okay. Try something else. Maybe something that rhymes with elimination. Go ahead, sir.
Take away the M.
Oh, yeah, elimination.
And
Nice.
the letters.
Sorry, I'm not good with words and all that shit. So, yeah, it's the elimination one. Okay, very nicely done, sir. All right. All right. So, yeah, I think this and the Boolean algebra stuff, and by the way, we're done because we got to the conclusion. I think this and the Boolean algebra stuff is going to be the toughest stuff. Okay. So, I know we're out of time, okay? For next class, do every problem that's on the assignment except for the very last 2, because we didn't go through 2 examples of this, and I want to go through those 2 examples. So just hand in, I think it's problems 1 through 10. Omit number 11 for now. We're going to finish those up, and you guys can just hand them in on, I guess, on Monday the following. Okay? So remember, guys, we're not coming here Monday, right? Because it's Labor Day. If If you do show up, you're gonna be the only people.
I'm lost. Which one do you want us to do?
I'll post it on Blackboard, but assignment 1, do every problem except for the last 2 problems, okay, the
Okay.
very last 2.
Okay.
Because they're just like this, and I wanna make sure we go through 2 examples.
Okay.
Alright guys, if you have questions, email me so I can help you out. I will see you in a week, hopefully, God willing.
So assignment 1 not due